Okay, so the grand finale here. Let's get down to quick review, functional groups. See if you can follow with me. Alcohol, you got that? Carbon connected to oxygen, connected to hydrogen. What comes next? Ether. Again, one oxygen, two single bonds, carbon group connected to oxygen, connected to carbon group. Alcohols and ethers, possible isomers of each other. We move up to aldehydes and ketones. Again, they're characterized by one oxygen, except now that oxygen is double bonded to a carbon. So aldehydes, again, a carbon on one side, we don't need the A designation. Carbon on one side, the carbon-oxygen double bond, which is the central focus, connected to a hydrogen. Ketones, again, very similar, except now the central focus, the carbonyl group, that carbon-oxygen double bond, has two carbon groups attached to it. All right, we move up to carboxylic acids, and now we're talking about adding two carbons in a specific sort of way. When we add two carbons, let's try to keep all those in view. Our central focus is the carbon-oxygen double bond combination connected to an oxygen with a single bond, and in an acid, on one side we have a carbon group, on the other side we have a hydrogen group. Ester, again we start with that same combination in the middle, the carbon double bond oxygen to an oxygen, but now what we connect, carbon group on this side, carbon group on this side. All right, so again, we don't need that A there because there's only one carbon group. So, just a quick review for these, notice the pattern. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. On the other hand, for the other combination, carbon, 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 carbon. Again, the distinguishing feature is that central connection point. Notice how that is the thing that differs between the alcohols and ethers, the aldehydes and ketones, and the acids and the esters. All right? Good. I hope that makes a little bit of sense to you. Now, our last two functional groups don't necessarily fit that pattern. They're pretty straightforward. We've got amines, which again are derivatives of ammonia. So think about ammonia, NH3. But we're replacing at least one of the hydrogens with a carbon group. So possibilities, carbon group connected to nitrogen with two hydrogens connected, two carbon groups attached to the nitrogen with one hydrogen connected, and then finally all of those bonding points to the nitrogen completely filled with carbon connections. So there are general formulas for the three possible types of amines. Again, this is primary, this is secondary, this is tertiary, and the focal point, again, just like above, the focal point is that central nitrogen and what's connected to the nitrogen in terms of distinguishing between secondary, tertiary, secondary, first primary, secondary, or tertiary amines. All right, the last functional group takes carbon and nitrogen and puts those together. The central feature, these are called amides. They have carbon and nitrogen, and they combine this feature, the carbon-oxygen double bond, with the nitrogen. And again, it's what's connected at these locations that distinguish. So we could call this R sub A, we could call this R sub B, we could call this R sub C, okay? Where those R groups can, in the simplest way, can be hydrogens, but more likely R sub A, R sub B, R sub C are going to be carbon groups. So that's an amide, and the feature of the amide is, again, this combination. Okay? And what distinguishes one amide or amide from the other is what is connected at those 3 locations. Now our job is this. Given a real quote-unquote molecule, let's scroll down, can we pick out the different functional groups? Can we identify those specific functional groups? Because each one of those specific patterns of atoms, non-carbon atoms, okay, adds a special function to the molecule. So for example, here's fructose. Fructose, a sugar found in high fructose corn syrup. Okay, fructose is naturally occurring molecule, high concentration in honey, for example. What do you see? Well, look here. I've got a carbon, oxygen, hydrogen. That is an alcohol. Matter of fact, if I look at fructose has lots of alcohol groups. There's an alcohol group. Don't let the wedges fool you. The wedges or the dashes are just an attempt to show a little bit about the 3-dimensional structure of these molecules. So, lots of alcohols. This is also an alcohol. What else do we have? Notice we have a carbon-oxygen double bond, and connection to that carbon-oxygen double bond is a carbon on this side and a carbon on this side. So what we have here is a ketone. So fructose is a molecule that contains 2 functional groups. It contains 4 alcohol functional groups, or excuse me, 5 alcohol functional groups, and it contains a ketone group. Okay? Notice that the backbone of the molecule is what? The backbone of the molecule is our carbon chain. Okay? So there's our carbon chain. So that's the backbone of the molecule. We've added additional atoms to add specific functionalities. So fructose has some of the properties of a ketone. It has some of the properties of an alcohol. Let's take a look at sucrose. Sucrose is the common name for sugar. C12H22O11. I'm guessing that you all have a little sucrose in your home. Perhaps in the morning you sprinkle a little extra sucrose on your cereal, or add a little sucrose to your tea or coffee, or whatever your favorite beverage might be. Or you drink a soda, which might contain about 40 grams of sucrose. Okay, sucrose, sugar. So perhaps the next time you're asked for somebody to pass the sugar, you might say, pass the sucrose, or pass the C12H22. What do we see in sucrose? Again, lots of what? Lots of alcohol functional groups. These are all alcohols. Notice the OH, carbon connected to oxygen connected to hydrogen. So lots of alcohol groups. And then do you see the other functional group? The other functional group is this one. Carbon connected to oxygen connected to carbon. Carbon connected to oxygen connected to carbon. Carbon connected to oxygen connected to carbon. Those are ethers. So sucrose is a mixture of, contains both alcohol functional groups and ether functional groups. Like most real molecules, they contain more than one functional group. Continuing on, we go down here. Here's wintergreen. We actually made this in the laboratory. If you've ever had a wintergreen lifesaver, you have eaten some of this molecule. So, what functional groups do you see? Well, starting off here, we see the OH, carbon, oxygen, hydrogen. That is definitely an alcohol. Okay, and then up here, look real closely. Again, remember that's a carbon. This is a carbon. This is a carbon. This functional group is a different color. Different color. This functional group is, I hope you got it before I did, ester. Again, as we look at that, I hope you recognize, first of all, that carbon-oxygen double bond connected to a carbon-oxygen single bond. And then you look a little bit more closely, you see that I've got a carbon on this side and a carbon on this side. That is definitely an ester. Okay? As a little sidelight, although it's not technically a functional group, notice again, we've got this beautiful 6-membered ring with the alternating double bonds. We've got the benzene ring. Okay? Really a common structure that appears in many, many molecules. All right, so essentially what we're doing now is we're using our skills to dissect a complicated molecule into its functional groups. Have you gotten a headache? Perhaps you need some ibuprofen. Here's the structure of ibuprofen, the active ingredient in over-the-counter medications like Advil. So let's do the analysis with ibuprofen. What functional groups do you see? All right, looking at it pretty closely here, the only functional group we really see is right here. Okay, everything else is hydrocarbon. I hope you identified that as a carboxylic acid. So ibuprofen has only one functional group, the carboxylic acid functional group. And again, comparing that to what we did before, we see the same structure, the carbon-oxygen double bond connected to a carbon-oxygen, but now on one side we have connected a hydrogen, and on the other side we have connected a carbon. So that is our carboxylic acid. Otherwise, it's all hydrocarbon, but again, I hope you notice that that lovely little benzene ring makes an appearance again. All right, more real molecules. If the ibuprofen didn't take care of your headache, perhaps you need some aspirin. So if we take a look at aspirin, what functional groups do we see? So I hope you've been able to identify two of those. Right here, what do you see? I hope you labeled that as a carboxylic acid. Again, we've got our carbon-oxygen double bond, carbon-oxygen single bond, hydrogen on one side, carbon on the other side. That's definitely a carboxylic acid. And then the other functional group looks pretty similar, except now this is not an acid, but it is an ester. I hope we can see that. Again, carbon-oxygen double bond, carbon-oxygen single bond. On the one side, we have a carbon here, we have a carbon here. That is definitely ester. All right, and of course, as we've seen in the other previous examples, we've got that beautiful six-membered benzene ring. So again, just like in the other molecules, we've got the benzene ring. Not necessarily a functional group, but certainly a very important structure in there. The benzene is a very common structure. Move over to aspartame. Aspartame is the artificial sweetener in many diet beverages. So let's take a look at that. As we start, what do we see? Let's see. First thing we see, perhaps, is the group right here. I hope we all recognize that as carboxylic acid. Again, carbon-oxygen double bond, perhaps is the first thing that catches our eye. Then we've got the carbon-oxygen single bond connected to a hydrogen. That's got to be a carboxylic acid. What do we see next? Color. So now we look here. Okay. Got a carbon here, carbon here, carbon here. So we've got another group here. This is carbon connected to nitrogen connected to hydrogen. That is our friend, the amine. Okay. Look a little more closely. We see carbon-oxygen double bond connected to a nitrogen. That is, altogether, that is an amide group. Okay, there's our amide. What else do we see? One last group. Look over here. Go to a different color. I hope everybody sees. Again, I've got a carbon here, I've got an oxygen here, carbon here, carbon here, oxygen connected to double bond, and again, I see that characteristic carboxyl group. I've got a carbon on this side, I've got an oxygen and carbon on this side. This is ester. And then, finally, that very common, beautiful structure there, our benzene group. So notice the prevalence. The last four molecules we've looked at all contain that special C6H6 ring. All right, tetracycline. If you've ever had an infection, you may have taken tetracycline. First of all, not surprising, it's called tetracycline. Tetra means four, cycle means four. What do you see here? 1, 2, 3, 4. So the common name tetracycline is an attempt to tell you that this molecule has lots of rings. It has 4 rings that are fused together. Lots of functional groups here. The predominant functional group is which one? Carbon, oxygen, hydrogen, carbon, oxygen, hydrogen, carbon, oxygen, hydrogen, carbon, oxygen, hydrogen, carbon, oxygen, hydrogen. We have lots of, altogether, alcohol groups. Okay? In addition, what else do you see? I see a carbon-oxygen double bond connected to 2 carbons. That is and I've got another one over here, a little hard to see. I've got 2, again, carbonyl group with carbons on both sides. I've got 2 ketones here. All right, continuing on, what else do you see? This is our most complicated example yet. I see a nitrogen here connected to 3 carbons. So there's a tertiary amine. We can just call it amine, but I like to show off a little bit. A tertiary amine. What else do we see? Finally, the last functional group. Can anybody nail that one? I see my carbon-oxygen double bond connected to a nitrogen. I hope everybody has labeled that one as amide. All right, and then finally, just again to refresh, we've got a benzene ring as part of that 4-ring system there in tetracycline. So again, complicated molecule, but from an organic chemistry perspective, we can break it down into its component functional groups. Each of those functional groups adds a certain property or function to the molecule, right? Do a few more of these. The next one, cinnamaldehyde. This is the substance that gives cinnamon its primary taste, and not surprising from the name, aldehyde. We're not surprised that we have an aldehyde group. Carbon-oxygen double bond connected to hydrogen, connected to carbon. There's our aldehyde. And again, we also have that ever-present, almost ubiquitous C6 ring. All right, continuing on. Are we having fun yet? Here's a molecule many of you have heard of, a molecule of great abuse, drug problems with this, methamphetamine, more commonly known as meth. Here's the structure of meth, and as we look at meth, first of all, what do we see? The only functional group that we really see is right here, and that is a nitrogen connected to a hydrogen, connected to a carbon, connected to a carbon. That is definitely an amine, and if we wanted to show off, we would call it a secondary amine. Okay? The meth part of this comes from the fact that we've got a methyl group there. So meth, meth, and of course, I don't want to neglect the fact that again we see that very special structure right there. So that's methamphetamine. If I'm giving you a headache, we could take some acetaminophen. Here's the structure of acetaminophen. This is the active ingredient in Tylenol. What functional groups do we see here? I hope everybody identifies that as alcohol, COH. I hope everybody has identified that as, should have used a different color. I hope everybody has identified that as amide. Yes. Carbon connected to oxygen, connected to a carbon, connected to a nitrogen. There's my amide. And then, of course, finally, another example of that very stable and ever-present C6 ring, the benzene ring. Whoa! Really quickly here, Taxol. Taxol is a naturally occurring substance found in yew trees that has been shown to be very effective at killing certain types of cancers, particularly breast cancer and ovarian cancer. And boy, we've got quite a few functional groups here. Can you pinpoint those? Okay, so I'm going to do this really quickly. I hope you recognize that as amide. I hope you recognize that, and that, and that as alcohols. Let me change my color. So this, and this, and this, alcohol. Okay. Whew. Where else are we going to go next? Let's see. What do we have here? This, and this, and this, and this are all what? I hope you said esters. Oh, what else we got hiding here? I think we have at least one more functional group hiding in here. That's the wrong button, excuse me. Let's see, what other functional group hiding in here? I have, oops, I missed theirs. Let's see. I have this, and that's the only one of those we have. That is ether. And then finally, I think there's one more functional group hiding in there. Let's see if we can pinpoint it. I've got this little dude right here. That is altogether, did you say ketone? Yes, that's a ketone. Wow. Not to mention the fact that Taxol has 3 of these lovely aromatic C6H6 rings. Okay? Good. All right. Look at the rest of those. Let you go through those. Okay? Picking out the functional groups. So here's the beauty of the functional group. Functional groups to the organic chemist are like the periodic table to regular chemist. Okay? Specific functional groups adds a specific set of properties to a molecule. And so therefore, irrespective of what other functional groups might be present, if your molecule contains alcohol functional groups, for example, it will share properties with all alcohols. If your molecule contains ketone functional groups, it will share properties with ketones. All right, great. Have fun with functional groups.